Welcome, everyone. Let me introduce our speaker for today's lunch presentation. So it's my pleasure to introduce Navraj Nendra. He is our speaker for this Snug Luncheon. Navraj Nendra is Senior Director of Marketing for Designware Interface and Analog IP at Synopsys. He has worked in the semiconductor industry since the mid-80s as an analog and mixed signal IC designer and manager. Navraj holds a master's degree in microelectronics from Brunel University and a postgraduate diploma in process technology from Middlesex University.
Thank you for the introduction. Great to see so many faces, so many friends actually. So I'm very happy that you're here. I was asked to give this presentation a few months ago, and I was thinking about what can I talk about that's kind of topical and interesting and will get people through their lunch without stuff being thrown at me. So I came up with this title, so hopefully you'll enjoy it. So I'm going to go back a little bit in my career. I used to work in a company called Philips, in Eindhoven, in fact. So that was the very formative part of my career. I was an analog circuit designer in a group that was doing analog front ends for digital audio. And so my customer were the digital engineers that were building the SoCs, and I was developing the analog front ends. And I worked both at the product division and also at a place called NAT Lab, which is their research center. And that's where I really kind of got to learn how to do analog circuit design in a digital CMOS process. So there were two things I learned at my time in Philips. The first thing, and this is very important, and it's the theme of the presentation, power, performance, and area must be met regardless of the semiconductor technology that you're designing in, okay? So when you're developing IP, when you're developing high-performance blocks, you cannot go to the foundry and say, hey, can you tweak this resistor for me? Can you optimize this transistor? Can you do something with this capacitor? You just have to live with that process because that's the process of the SoC, okay? So that was the first thing I learned. The second thing I learned was a little bit of Dutch. Dutch is a very complex language, but I did learn how to have a good meal in Dutch. So the expression is smakelijk eten. So please, smakelijk eten, enjoy your lunch. I'm going to give you a little bit of a primer on FinFET technology and some background as to how I came up with the title of designing 7nm IP, Bring It On More. Then I'm going to get into some physics. And I'm going to try and make it light, entertaining, and interesting, but it's physics after all. It's important to understand how those physics apply themselves to foundation IP. So I'm going to take physics, take those equations, and make some memories and libraries, which we call foundation IP. Okay? From there, we're going to move into interface IP. For interface IP, I'm going to talk about both the transaction layer, so the digital IP, and also the PHYs, the physical IP. I was speaking with our VP of Engineering, Ralph Morgan, that develops all the digital IP at Synopsys, and I said, Ralph, I'm doing this lunchtime presentation on 7nm design, and you, as the most experienced, knowledgeable person on digital design at Synopsys, as far as IP is concerned, are there any impacts to the process technology on digital design? And he said, of course, and he gave me some very interesting insights on how process variability is impacting digital design. So I'm going to combine digital design with PHYs, and that's the section on interface IP at 7nm. Then I'm going to turn it onto the second part of the presentation, which is about bring it on more. And you'll see what that means as we talk through the presentation, and then we'll get into the summary and acknowledgements. Okay? So as a primer, to give you a little bit of introduction, a few things are happening, okay? So this particular representation shows how transistors have been scaling from one micron, so that was the time when I was working at Philips, to 7, maybe 5 nanometers. There were some innovations in material science that made that scaling happen. So if you remember, some of you may remember the big copper interconnect debate at 180 nanometers. And then around 90 nanometers, There's a lot of conversations about getting the speed up of the devices using strain. In semiconductor physics, strain or stress is good because it makes your devices work harder. And then, as we all know, it's public information. Intel first announced the implementation of high-K metal gate devices on about 45 nanometers. And then 2 years ago, I had the opportunity to do a lunch presentation here at Snug, and I talked about FinFETs. And at the time, we were talking about 22, 16, 14 nanometer FinFETs. Okay? So that's the trend of transistor scaling. You can think of them as 3D transistors. Okay? The bring it on more piece, which is interesting, is that as well as all this scaling that's happening, people are looking at packaging technologies. People are looking at leveraging maybe a design that was done on 28 nanometers or 16 nanometers, keeping the design as is, and then using some kind of interposer technology to connect to the high-performance die that's developed in the 7 nanometer technology. So that, for me, is my sort of representation of the bring it on more technology. So technologies like interposer, high bandwidth memories that leverage a common substrate with 2 different die. Okay? So 3D transistors, 2.5D packaging, bring it on more. There's something very interesting about this slide. If you look at the orange line and you look at the purple line, they don't quite follow each other. So up until about 180 nanometers, if you were an engineer and you said, hey, I'm designing in 180 nanometers, that's what was actually being manufactured. That represented the effective channel length. And then something weird happened. The fabs started innovating more, right? They started introducing new materials. The L effective actually became smaller than the node name. L was in sync with the technology node. L accelerated, and then it started to saturate. This is a very interesting point to consider. At this time, in the market, there was a move to the fabless semiconductor industry, right? So you had fabs coming up. You had fabless companies starting. These fabs wanted to attract those engineers to that fab. So it became a marketing exercise to describe which technology node you're working in. So L accelerated and then saturated, and then now, today, when we talk about 22 nanometers or 14 nanometers or 10 nanometers or 7 nanometers, it has no representation of the effective channel length. In fact, if you look at the purple line, they all look the same. Let me get into a little bit more detail, right? So what I said was that the scaling node name is fuzzy, but if you look at the gate pitch, that's a more accurate representation of the technology feature size. So the technology node definition varies from one fab to another fab, okay? But the gate pitch definition is precise and meaningful. And this is used for standard cell library development. So what I did here was I took that purple line from the previous slide and I represented it in that purple bar. So you can see, if you look at the fuzzy circles at the top, 14 nanometers, 10 nanometers, 7 nanometers don't actually represent anything in terms of the technology size. It's all to do with the gate pitch. So the gate pitch is the most important dimension when you're looking at the feature size of the technology that you're working in. I'm going to move into a little bit of a refresher of FinFET technology before we go deeper into 7 nanometers. This is a representation of a FinFET device. The concept is that the multiple gate surrounds a very thin channel that can fully deplete it of carriers. What this does, it gives it much better electrical characteristics. SCE, the short channel effects, are better controlled with FinFET devices. You reduce some of the horrible things that were happening at 20 nanometer planar, like drain-induced barrier lowering and the subthreshold slope. Both of these points are related to electrostatics, and I will get into more details in the later part of the presentation. Also, the lower VDD was used to target a lower ion I-off. Okay, so here you see a complete representation of 3 fins fully surrounded by 1 gate. So what are the advantages of FinFET devices? Okay, lower leakage because of the reduced drain-induced barrier lowering, and because of the better subthreshold slope. Less variability caused by random dopant fluctuations, less VT variability. Okay? The lower operating voltage gives you about 50% better dynamic power savings. Great, wonderful. That moved us from 20 nanometer planar to the FinFET node. There were some considerations of FinFET devices. There was a change in the way you do design work, okay? So these considerations included the quantized widths and channel lengths. Body biasing, if you were using that in your memory designs, became totally ineffective. You got more parasitics. You had a 3D structure that changed the way you understood the parasitics. There were problems with aging, mostly related to NBTI, the negative bias thermal instability. It was a bit worse than planar. There were potential self-heating effects, and ESD needed to be considered as a bigger challenge with these devices. That being said, when I presented this 2 years ago, we hadn't many silicon proof points. Today we do. These are all the silicon proof points that we have on 22, 16, 14, 10. Okay? We've been working with a number of different providers of FinFET technology, as you can see from the list here. We've done a bunch of tape-outs to prove that these IPs work. The other key point, I'm bringing up PPA, power, performance, and area. Okay? We achieved better power, performance, and area over 28 nanometers using the FinFET technology. All right, I'm going to move into 7 nanometers now. So this is when it gets more relevant to today's presentation. So here I've got 2 representations of a 14 nanometer device. Again, I'm not picking on any foundry here. So 14 is a representation that we talk about in the industry. And then 7 nanometers. Again, I'm not picking on any foundry here. The key point is that you want to maintain a certain aspect ratio to prevent or mitigate against short channel effects. That aspect ratio, L over W, is 2.5. Okay? So diagrammatically, this is what it looks like. Simultaneously, in order to get performance, the fins are getting taller. This gives you more current per layout area. Let me show you how that works. Okay. Here I've taken a representation of moving from a planar technology all the way to 7 nanometers, and I'm showing you the extrapolation of the fin height. Okay? So you see that when you're getting to 10 and 7 nanometers, the fin height is, in this dimension of about 50 or higher than 50. Okay, the aspect ratio also increases, but the point is that you want to keep the channel length and the fin width about 2.5. So I was actually discussing this with one of our scientists, Victor Moroz, and he was trying to explain the concept to me, and I was scratching my head. So, Victor, I don't quite understand, and he showed me this picture. So he said, look, just think of the planar device as the first part of evolution for mankind, and think of the 7 nanometer device as the Homo Sapien. Okay? So at Synopsys, we're a very professional and thorough company. When I have to do presentations like this in front of a large audience, I've got to rehearse my presentations. And when I did my rehearsal, I presented this slide, and somebody said to me, what comes after Homo Sapiens? The answer's very easy, actually. It's Mork from Ork, right? So what happened here is that what's after 7 nanometers? Mork used to say nano, nano, but he should have said nanowire, nanowire. So what comes after 7 nanometers, from my perspective, according to my friend here, Mork from Ork, it's going to be nanowires. So this is Robin Williams, rest in peace. All right, I gave you a primer on FinFETs. I give you a little bit of introduction to 7 nanometers. I'm going to pause for a little bit here and just stress upon the key points. First one. Moore's law drove innovation to achieve scaling, both at the transistor level and at the system level. So I talked about the 3D transistor. I talked about 2.5D packaging. Some people talk about 3D packaging, okay? 3 generations of FinFETs have been demonstrated after planar. So you had the 22 nanometer FinFET technology, or Tri-Gate technology from Intel. And then you had the commercial foundries like TSMC and Samsung with their 16 and 14. And now we're talking about 10 and 7. So 3 generations have been demonstrated after planar. I also showed you that there are many silicon proof points now on 16, 14, and 10. The fin height, I gave you the example there, it provides performance and area benefits. So at 7 nanometers, it's all about the fin height. And finally, as part of my introduction here, the node definition varies from one company to another. So I'm talking about 7, it could equally apply to 10. Okay, let's move into some physics. And I'll take that into the foundation IP. All right, so I'm going to introduce some terms. So firstly, I'll start easy. I'm showing you a picture here of a logic chip. Sorry, I'm showing you a picture of a standard cell library. Logic chips are based on standard cell libraries. The standard cell is defined by certain parameters. Gate pitch, or CGP, also known as the contacted poly pitch, metal pitch, fin pitch, okay? This is how you typically route on the standard cell basis. These are the ways these dimensions form themselves on the standard cell. So if you were to do a little bit of mathematics now, if you multiplied the gate pitch with the fin pitch, that gives you the transistor area, okay? If you multiply the gate pitch with the metal pitch, it determines the cell area. If that's not meaningful, basically what I'm saying is that if you're looking at a 12-track cell, it's easier to route than a 7-track cell, okay? So I'm going to take some of those concepts, I put them in a table, and I'm comparing 3 different generations of FinFET devices, 14, 10, and 7. At these critical dimensions, resistance and process variations have an increasing effect on the RC performance, okay? The contact reduction in terms of area increases the series resistance, and that's what you're seeing on this slide. If you look at these advanced nodes, it's possible to scale the metal pitch to less than 40 nanometers using multi-patterning, okay? So when I'm talking about 7 nanometers today, I'm still assuming standard 193 lithography techniques. Resistance process variations, as I mentioned, really require an increasing performance, really require attention to the RC performance. And finally, if you look at the way this is manufactured, the contacted gate pitch and the metal pitch will give you about 0.5 area scaling node to node. And that was the purpose of showing you the previous slide when I did that quick calculation. This table is actually available from IMEC, okay? So I'm not showing any foundry-specific information here. So let's take that concept of area scaling a little bit further. On this graph, I've got the metal pitch and the contacted gate pitch. There's 2 axes. I'm showing 28, 16, 14, 10, 7, and 5. I'm showing you the ratio, I'm showing you the coordinates of the contacted gate pitch and the metal pitch. So you can see those numbers by the dots. So with this format, you can scale by about 0.5. However, there's enough learning today to use another technique, as well as increasing the fin height to get performance. The other technique is called fin depopulation. So you remove the fins after you make them taller. Fin depopulation reduces the dynamic power significantly, as well as increasing speed and improving the overall speed power metrics, power delay product, PDP. Okay? There are further interesting things that are happening. People are starting to use routing optimization, air spacers. That also helps to improve the power delay product. Towards the end of the presentation, I'll show you some interesting work I got from Qualcomm. They were very happy to allow me to show that information, where they actually trade off different types of routing optimization with air spacers to improve the PDP for 2 different types of 7-nanometer technology. So a node-to-node speed improvement of 20% is used as a target for high-performance devices. So I'm now starting to introduce another concept here. So I mentioned fin height, I mentioned fin depopulation, and I mentioned that foundries are starting to play with the electrostatics in order to increase the speed. So now you can have a low-power version and a high-performance version of that latest generation of FinFET technology. So I'm going to talk about the node-to-node speed improvement on this particular graph here. Again, 28 as your reference point. This is dynamic power versus frequency, 14, 10, 7. So you saw a dramatic increase in speed moving from planar 28 to the first generation of FinFET technology from a commercial foundry perspective. And then you see, depending on how you play with the electrostatics, a 20% improvement moving to the next generation of FinFET nodes. Okay? So this example shows a ring oscillator with a fan out of 3. It's a 9-track library with no back-end of line load. Okay, I'm going to go back to my table because I want to highlight something related to electrostatics. Okay? I mentioned a couple of things at the beginning of the presentation: drain-induced barrier lowering and sub-threshold slope. Okay? Basically, for a physicist, what you want to do to maintain performance in the technology is that you want to maintain about 70 millivolts per decade for your sub-threshold slope, and about 50 millivolts per decade for your drain-induced barrier lowering. Okay? If that's complete gobbledygook to you, basically what I'm saying is that those 2 parameters give you a good switch. Okay? The sub-threshold slope represents the behavior of the switch in weak inversion, and the drain-induced barrier lowering represents the electrostatic behavior of that switch due to a drain bias when the threshold voltage starts to vary. So the target drive current per fin needed to reach the target speed for 7 nanometers can be attained for those various back end of line effects like the R and the C, depending on how you trade off your electrostatics. So that's a key point. These trade-offs will give you the high performance, latest generation of FinFET device and the low power version of that FinFET device because of the way you trade off the electrostatics. Target 7 nanometer speed can be attained for various parasitic capacitances and series resistances. I talked a little bit about physics. I can talk more if you're interested, but the organizers won't let me, so I'm going to move on to foundation IP with that learning. Okay? This represents a view from the company I work for, Synopsys, of foundation IP, high speed, high density, ultra high density. And based on some of the learnings that I've just shown you, you can build some very interesting foundation elements, like a dedicated high-speed logic library with 9 tracks, to a high-density 7.5-track library. You can go into ultra-high-density logic libraries. That's great. I've made a little bit of a comment here about scaling beyond 7 nanometers. This doesn't apply to going to nanowires. What I'm saying is that you can, as an IP developer, you can actually eke more performance out of those devices by having special memory and library elements in your standard offering. From our terminology, we call it HPC, which is called High Performance Core Design Kit. And this we've benchmarked on previous nodes. For CPUs, we've used very popular CPUs, GPUs, DSPs, and we're getting very, very good PPA using the 7 nanometer devices as we speak today. I'll go into a little bit more detail about what these things look like. Also at 7 nanometers, scaling beyond that node, we've got ultra high density single port register files, and these replace synthesized latch memories. These are custom, handcrafted, very small density memories that enable even smaller memories and synthesized versions. So I'm going to go into a little bit more detail about what these things look like. So these are 7 nanometer specialized cells as part of our foundation IP development. So here I've put segments for CPU, GPU, DSP, and you can look at things like high-speed flops, special clock drivers, delay cells, metastable optimized flops used for synchronizers. And all of these things have been designed specifically for 7 nanometers in order to optimize the performance of those particular elements. Another challenge that we're seeing is customers are trying to push down the core voltage to a point where things start to not work. Okay? For memory compilers, we're looking at read and write assist technology that can support a minimum voltage lower than the rated voltage that's given to you by the foundry. So this represents around 630 millivolts supply. And so on the left, you see the technology without write assist. Again, these are memory compilers. Okay? Without write assist, we see failures. So in this particular example, you won't be able to read the text, but I can read it from here. You're basically looking at about 230 fails in 10,000 Monte Carlo runs with a 0.63 volt supply. When you up it a little bit to 0.7 of a volt, you get a handful of failures when you do it over 10,000 times running Monte Carlo. The point is that the DC write margin shows one fail at about 720 millivolts in 100,000 runs. So as you increase the voltage towards the rated voltage of that 7 nanometer technology, you don't need the assist technology, but when you drop, you do, right? So with the write assist technology, we see no fails at 630 millivolts. And this is run over worst case PVT. If you're interested, if you know something about memories, the bit cell flip time is about 400 picoseconds, less than 400 picoseconds. So we're taking the 7 nanometer technology and we're doing more to it to enhance the value of the foundation blocks. Actually, I noticed Yervant walking into the room, so hopefully I'm representing your technology very well, Yervant. If you don't know Yervant, he's a fantastic engineer for test technology, so someone that you should really get to know, and very lucky to have him working as a colleague at Synopsys. So I asked Yervant, said, hey Yervant, I'm doing this presentation, and are you seeing any defects on the 7 nanometer devices where you can model them and then apply them to the embedded self-test and repair technology that we have for foundation for memories? He said, yes, of course. There are lots of new defect elements that are coming up that are specific to 7 nanometers. And this is what we discussed. So basically, you have process variation, some generic things like process variation, systematic random faults. But really, it's related to that fin height, as I mentioned. The fin height, interestingly, creates width variability. So that's an issue. That's a defect that needs to be modeled. You've got lithographic issues with the contacted poly pitch and the fin pitch. Okay? The resistance and the parasitic line capacitance also are different, very different to 10 nanometers, and they're very critical at 7. And so these are modeled in the fault repair technology. And so all of these things have been implemented in a test algorithm, and they're helping to ramp 7 nanometer technology with quality and yield. And this is because we have access to the FinFET devices. You can only do this if you have access to the FinFET devices. So I'm going to finish up with some key points. Again, we talked about 7 nanometer scaling, moving to foundation IP. I talked about this concept called fin depopulation. You'll start hearing more about this as we move more into the 7 nanometer technology. So fin depopulation, it lowers dynamic power while preserving speed and reducing density in your standard cells. You can get an additional speed improvement. As a placeholder, I've put 20% because that's what I've seen in research. And this is possible as there is enough electrostatic control, right? You're playing with the sub-threshold slope and the drain-induced barrier lowering, so 70 millivolts per decade and 50 millivolts per decade, and you're trading that off with the back end of line resistance and capacitance in order to create a high-performance device and a low-power device. What we've done is we've created some specialized cells and assist circuits, and they extend the performance beyond 7 nanometers. And we've got new memory test algorithms that are being developed by Yervant's team to ramp quality and yield. Okay, so I'll move from physics to foundation IP. I'm going to now talk a little bit about interface IP. These are some of the IP blocks that I work on at Synopsys. This part of the presentation talks about the digital transaction layer. As I mentioned at the beginning, the 7-nanometer technology, because of the variability, impacts digital design. And I'm also going to talk about PHY development at 7 nanometers. Okay? So at a high level, reliability, you've got nodes that are getting smaller, lower supply voltages, clock frequencies that are going up, clock domains that are increasing. In the next 2 slides, I'll show you some statistics we ran at Synopsys of customers and how their clock frequencies are going up and how the number of clock domains are increasing. Higher density circuits, the issues with the threshold voltage, so basically the variations in critical dimensions, random dopant fluctuation, you've got voltage variations, you've got both positive bias thermal instability and negative bias thermal instability. The positive bias thermal instability impacts the hot carrier injection. That being said, the interesting thing with 7 is that you can optimize each of these blocks by exploiting timing speculation, by looking at clock, signal, power gating, and dynamic voltage frequency scaling. Okay. So I mentioned clock frequencies going up. I won't say too much about this slide. It's just very impressive that you, our customers, are designing chips with frequencies going up to in excess of 2 gigahertz. That's pretty cool. So it's very enjoyable to be part of this development with our customers when they're pushing the envelope in terms of speed. What was interesting, actually, and this is a complete aside to the presentation, I was looking at my slides last night as part of the preparation, and I noticed that at the lower speeds, so if you look at the 50 megahertz, 100 megahertz, 200 megahertz, there's an uptick. And do you know what that is? It's related to IoT. So customers are starting to develop new products that require lower frequencies, namely IoT. I promised myself I would say IoT once in this presentation, so I did. So I'm coming from the analog mixed signal world, and we barely have a clock. But this just totally blows my mind. So this is basically data from our customers. This is over 500 people that were surveyed by Synopsys, and it says here that a lot of customers are using more than 20 clock domains. And if you look at the right-hand side, 7% of our customers have more than 1,000 clock domains on their SOT. That blows my mind. So I looked at this and I said, okay, how does that impact digital IP development? So we'll look at these 2 factors now. So the point, when you've got lots of clocks, lots of clock domains, you've got to balance them over your big SoC. Okay. Remember, with these advanced technology nodes, there are parameter variations across the chip. It makes it very difficult to control delays, especially in your clock networks and any other global signal. So what's happening here is that people are starting to move to GAL, okay? Globally asynchronous, but locally synchronous designs. So this is a technology that's, 20, 25 years old, but GAL is now being implemented again, both at the SoC level and at the large IP level. So when we're developing our big, more complex controllers with a connection to an Amber bridge, for example, that's a lot of gate count. We're starting to look at this type of technology to solve some of the large parameter variations. The clock net power is very dominant. You've got to manage the clock skew over multiple corners. And then you do asynchronous data exchange, again, going back to the GAL concept, by having dedicated synchronous blocks and handshaking asynchronously between them. So that's one issue on digital design. The second issue is really looking at timing constraints. So here I am actually giving you a real example that we're working on today in my company. We have a lot of USB development, USB IP development, and this is an example of a USB system with the PHY and the controller. And here, in order to solve the problems with timing constraints, we did 3 things. We added ring buffers into the architecture of the pipe interface. So you see the pipe interface between the PHY and the controller. And so that helped in managing the timing constraints between the RX-TX paths and made it operate functionally. So that was one thing. The second thing we did was we separated the function into two voltage domains that would shift depending on the power mode. And the third thing was related to the hold time challenges. And basically, with the hold time challenges, we had to come up with a new architecture to solve that problem. If you're interested, I can share the details of the architecture, but in a public audience, I'm not able to do that. Razz, reliability, accessibility, and serviceability. Okay. Again, this is digital IP. Process variability, lower supply voltages, higher clock frequencies impact the reliability of the design. What happens is that now, with these advanced nodes, you're seeing RTL development with a lot of redundancy. In fact, looking at some of the development that's going on today for consumer products, they almost look like the work that was done some years ago for defense products in older nodes in FPGAs because of the amount of variability in the leading edge nodes, so that you have to add this design redundancy. You've got to identify your critical registers and states. And this is great because I work at Synopsys. We also have a big tools franchise. Our IP team can work with the EDA team and share some of the challenges that we see in the IP development to help enhance what's going on in the EDA world. And some of these things are included here. So we're looking at new functions because of the redundancy and actual replication of the circuits that you're doing in RTL to solve the variability problem. You can add, through the tools, triple modular redundancy. You can look at Hamming 3-distance state machines. Not only at the RTL level, but this must be preserved in your back-end flow. So IP and EDA changes are needed to protect the data paths and state machines. So this is what I'm talking about, Razz. Reliability, availability, serviceability. Reliability, avoid, detect, and repair. Availability, stay operational. Serviceability, diagnose the system should you get a fault. So I'm going to take that concept of Razz and apply it to two examples, a PCI Express controller and a DDR controller. So here's something that we've done for those two blocks. So we've implemented ECC, right? Data protection. So parity ECC gives you data protection. This is used in conjunction with a protocol. It needs to be protocol specific. It corrects errors in the data path and the RAMs. Event counters are used, and they monitor the system availability. And then we leverage error injection and silicon debug capabilities to diagnose a system during system recovery. So this particular picture, it was from a white paper that we wrote, and it describes using ECC for a PCI Express controller. So here, basically, the concept is that with on-chip CPUs in SoCs, they routinely have about 64-bit data paths. So there's a data overhead for the ECC compared to the parity. And this disappears in this particular example. So it means that you can add ECC without impacting area. So I talked about digital IP. I'm going to move into my comfort zone, which is analog mixed signal. I presented this slide 2 years ago. Nothing really has changed in terms of what we're seeing on the impact of 7 in terms of the schematics and the electrical parameters. So the point is that, for an analog mixed signal developer, the key parameters are GM, the transconductance, GD, the output conductance, FT, Fmax, matching and noise, okay? So what we're seeing is that the drive strength is similar for the PMOS and NMOS devices. Device matching is better than planar, even at 7 nanometers, although we do see a variation in the oxide thickness and the work function along the fin heights. The aspect ratio is mapped to the gate length and the number of fins. Because of the quantized device sizes, you still have to bin the way you architect a schematic. When you're doing high-speed blocks, the challenge really goes back to the fact that you've got quantized devices stacked. They're stacked. They increase the number of parasitics, which requires a new design for high-speed blocks. Here in this picture, what I'm showing is the gain, the intrinsic gain. So the intrinsic gain is the transconductance over the output conductance. of bulk, which is represented in blue, and FinFET, which is represented in red. And this example is still relevant in 7 nanometers. So you can see you still get better gain with the 7 nanometer FinFET device. What about layout? Yes, there are lots of changes in the way people look at layout. So the number of restricted design rules has increased because it's a challenge to meet the line widths of 7 nanometers. Okay? So if you want to go into a little bit more detail, what I'm saying here is that the lowest layer metals can only go in one direction. Okay? So you can't basically route like this and then do this, or jog and do that. You've got to basically go like this, stop, put your via, and then go up. Okay? So the lowest layer metals can only go in one direction. Routing in non-preferred orientations is very difficult. And if you've got a long length of P devices and N devices and you want to hook them up through the gate using poly, it's not allowed. You have to use metal. So there's no local interconnect of poly. The other interesting point is the active layers, diffusion, gate, poly, have shrunk faster than the metal interconnect. It's quite funny, actually. So when we first started working on this, we compacted the 7 nanometer transistors, really tight because you can, right? But they were so small that you couldn't route to them. So today, it's counterintuitive, but you've got to think about your routing channel and then fill the devices in around the routes. This example is a advanced node 7 nanometer USB 2 PHY that we've been working on. Multi-patterning increases layout effort significantly, okay? So basically, this is a little bit like a design guideline, okay? All implants have to be on a certain grid. Thick gate devices can only be connected using metal, so that applies to my previous point. There's a lot of stipulation around the diffusion space and cut metal. Double patterning, cut metals, diffusion space really have an impact on the way you look at your layout. You can't use, rectangular metal can only go in one direction. And to help us, and again, like in the digital world, we have a large franchise on analog tools as well. So we've been working with our analog design team to support some of the challenges that we've seen on the IP development side into the new tools. This example shows triple patterning using 3 steps of litho etch, okay? And its color, it's mapped to the color of the particular lithography mask that you're developing to, okay? So this is the tool that I mentioned that we're using to develop some of the analog mixed signal IP. It has a good install base, a lot of great collaboration between the IP development team and the custom compiler team to support custom development on 7 nanometers. One of the key things that I like about this tool really is the ability to do electromigration, IR drop prediction before you actually do all your layout. So that's a really cool facility that you don't have to go all the way to layout before you see the impact of electromigration, which is actually increasing on 7 nanometers. All right, what you really want to see are the proof points, and we have some on 7 nanometer, okay? This is an example of the latest version of USB 3. It's called USB 3.1, runs at 10 gigabit per second. It's using a form factor called Type C, okay? This particular design actually has support for another function called DisplayPort, so it's a combo PHY. It goes to 10 gig, as I mentioned. It's smaller than the previous generation of FinFET technology, okay? That's a key point. And it has certain performance characteristics related to the loss of the channel over a certain distance. We've represented the technology with equalization, right? So we're looking at decision feedback equalization and some linear equalization in order to support a channel that's needed for USB 3.1. Going back to the digital world for a little bit, what's happening is that people are starting to implement some kind of USB functionality in their big network servers as a trace and debug port. I've tried to explain this in a really kind of simple graphical way. So if you look at that big horrible picture on the left, that represents how people do trace and debug today, okay? If you look at the picture on the right, that represents the Type C connector, okay? Then if you look at the picture at the bottom, this is actually something I got from Amazon. It's one of the Apple products. The little connector, the smallest connector on that side view, that's the Type C connector. That Type C connector does everything you need to do 10 times faster with less area than that big horrible connector that you see on the left-hand side. This whole thing is being orchestrated and managed by the MIPI Alliance. There's a special set of protocols related to the debug. It's called the Debug Working Group. So the point is that you get more throughput with 10 gigabits per second for debug and trace. It's being standardized using a USB cable and a PC. And this particular example shows the USB 3.1 from Synopsys with our device controller. There's also in this diagram an external buffer control that allows extended trace data to be output under hardware control. Okay? So this is happening today. DDR, high-speed memory interfaces. I've picked LPDDR4 here. Again, it's a 7-nanometer proof point. This is running at 4267 megabits per second. It's designed to work on most common requirements in terms of PCB, UDIMMs, SODIMMs, so soldered down DIMMs. It has a very unique technology for training. It's based on a microprocessor. Okay, this does basically all the compensation that's required. There are a number of states that are available which optimize the frequency and the power. It has VT compensation. It has I/O equalization, and this particular architecture you can place on the east-west part of the die or the north-south part of the die. So remember what I said about 7 nanometers having orientation restrictions? This particular design gets around that by the way we've orchestrated the architecture. I mentioned diagnostics in the context of USB 3.1. This particular development also shows you the eye directly at the DRAM and at the IP level. So you can look at the eye directly from the silicon for every bit at the DRAM and at the host. This is firmware based. It's in a 2D format. And I think it was Saturday. I've been working late on my slides, and my family were kind of intrigued about what I'm doing. So I said, okay, I'm going to run my presentation by you. You know, my family's not involved in high tech, so it's kind of interesting. So I have a 3-year-old son who's kind of talking a lot now. And I got to this slide, it's slide 44, and they didn't have the luxury of lunch either. So when he saw this slide, he goes, "Papa, look, America flag." So, so it must be the red, white, and blue. So there you go. It's made in America, the DDR IP. And it'll feel like the 4th of July when you bring it up, because you see all these beautiful light diagrams. Okay, PCI Express, 7-nanometer proof points. Again, I stress on the power area improvements compared to previous nodes. We also implemented equalization technology. This uses the core and the I/O voltage. The I/O voltage we can bring down to 1.5 volts, and it has some key features that are required for that particular market. If you're interested, I'm happy to go into a lot more detail about these particular IPs after the presentation. So key points. Razz, reliability, addressability, serviceability, sorts out all the processability issues in digital IP. The layout effort has increased in these advanced nodes, mostly due to the restrictive design rules and multi-patterning. There has been an improvement in power and area compared to previous FinFET nodes. Most of that improvement has come through architectural changes in the IP. Finally, you can see that we've used the opportunity to add more to the IP, like silicon diagnostics, eye monitors, trace and debug. Okay, let's bring it on more. So this is another interesting conversation that's happening in the industry around new packaging and IP technologies. 2.5D, 3D interposer, HBM is the IP that's used in this configuration. And here I've kind of given you an example of a 2.5D construct with a common substrate and 2 die that are talking to each other through some kind of on-chip interposer or TSV. Okay? So here they call it a smart silicon interposer and a 3D TSV. So if I take that example, I'm going to apply it to IP, because that's the area that I work in. And this is an example of the HBM connecting to a DRAM on an interposer substrate with a package substrate below. And this is actually happening today with graphics applications. So if you look at AMD, for example, they're shipping graphics boxes with this technology using HBM. It can also be used in networking applications for last level cache. So what does this look like in terms of IP? So this is a picture of the HBM2 IP that we've been developing on 7 nanometers. Okay, it's interposer based. It can go up to 2.4 megabits per second. As you saw with the LPDDR4, it's half the speed, but this is a massive interface, very, very, very wide. So it gives you terabits of speed. There are 8 independent memory channels. You can go up to 8 DRAM stacks. It has a standard interface. There's power management modes. And the DFT is interesting because you can do at-speed loopback. You can do asynchronous bypass through the whole chain. It has digital and analog test point observability. And you have probe points for power delivery to allow wafer sort testing. So this thing has been designed for production. The key point is that it reduces power per centimeter cubed. All right, summary. I'm going back to that reference I made at the beginning. This is a paper that was written by Dr. Song and his team at Qualcomm. And I was chatting with him a few Sundays ago, and he said, yes, feel free to use the paper. And so it's published in the VLSI conference last year. And he did some interesting work here. So this is basically a smartphone usage module based on battery consumption comparison. So basically, people use the smartphones for YouTube, browsing the web, doing emails, and then quite a bit of the time it's actually doing nothing in standby mode. What his team did was they compared 3 technology nodes. But the interesting point here was that they compared 2 versions of the 7 nanometer. And this is theoretical. It's not any foundry-specific information. But if you read the paper and you speak with that team, what I learned was that for the comparison they made, they really were able to trade off the power consumption based on thin depopulation, wraparound contacts, air spaces. Okay? So very interesting. So they, again, did what we did at Synopsys with our foundation IP. They were able to optimize certain parameters to get even more performance out of that leading edge node. All right. To summarize the presentation, so hopefully you kind of believe me now that the 7 nanometer proof points exist. They exist for interface IP and foundation IP. I gave you examples of what we've done. It was an opportunity for us to do some things like improving the area and power and also add more features. So at a very top level, we added more stuff, but we got the power and area down at 7 nanometers. And the bring it on more is all the system level innovation. And this includes interposer and HBM2. Before I finish and we go on to the other parts of the lunch, I just want to give some acknowledgements. One of the fantastic opportunities I have working at Synopsys is that I work with all these great people. It's just a pleasure to learn from all the different expertise that we have in the company, and I'd really like to acknowledge everyone here. So I'll take a few seconds to have you read those names. And then references, if you're interested in learning more, I have them here. And then finally, I used a lot of acronyms. 2 years ago, I only filled up half the slide when I did this presentation. So maybe if I get invited next time, we'll fill it more with acronyms. But you have the acronyms. The most important one is power, performance, and area. So thank you very much.